Recording is rolling. It is Wednesday, September 3rd. So yesterday at the end of class, I was going through these posters. I got most of the way where I wanted to go. So pull us out. We'll finish us off. All right, probably good review anyway. I was looking at your guys' AP classroom questions that are due. Well, right now I have the due date that's coming Monday. Okay, which is a lot of linear motions, but there are a few projectiles. Okay. And I want to make sure I got everything checked off. There was one or two questions involving relative velocity, so I do want to cover that with you guys. I do have a car and truck FRQ in front of me, so I will hand this out to you guys, and we'll be doing this, and then for this class. Now, my earlier class, that's about where time ran out. I wanted to do a reaction time lab with you guys, where you guys get in pairs and drop a roller, catch a roller, but we'll have to save this for another day. Yeah, I do want to start projectiles tomorrow, so that's also on the plan. And then, guys, look for a kinematic motion quiz by the end of next week. Now, kinematic motion is linear motion and also projectile motion, okay, which all involve just these three, or like if you want equation form, it's just these equations. Okay? Of course, there's probably some graph questions too, like what is velocity versus time graph. So, like, I think. All right, so you guys good with the agenda? What we're doing? All right, so look at these posters here. Where was I? Flip through. Well. Right here. Maybe I'll just pick up from here. Okay. So we got these three kinematic formulas that will relate 5 variables. Right? We got time, acceleration, displacement, initial velocity, final velocity. Okay. The top one tells you the relationship between distance and time, basically. This one, velocity versus time. This velocity is a function of distance. So some version of that. You can't identify any three, stop the other two. Yeah, I did score your guys' linear motion puzzles, and I passed those back to your folders back there. Overall, you guys did pretty good on those. So it looks like you guys have a pretty good idea of what's on there. Okay. Drop ball off a cliff. So watch your time tick in, watch it take for 5 seconds. Gravity field will be constant. That's the type of acceleration. The velocity picks up well at the rate of acceleration. So this would be v equals gt, right? V equals gt gets you this column. And then, guys, how far something falls? Isn't that x equals 1/2 at squared? Okay. Which is really now, guys. Word drop. Guys, word drop means the initial velocity is 0. So if you let this bit go to 0, is that, hey, that h equals 1/2 gt squared, isn't it? Is that the college equation right there? College? That's that one right there. Right? There's that. So after 5 seconds, it's about 125 meters feet. How do you know that? College? Right. So 1/2 gt squared. If you take this table and you turn this into graphs, x versus t, v versus t, a versus t, you get these graphs. Now, guys, in an accelerating environment, you tend to see position versus time be, what shape is that? Parabola. Velocity first time is pretty much always going to be linear in this class. There's some version of lines, straight lines. Okay? And acceleration in this class should always be constant values. Okay? Sometimes acceleration is 0. Because if the acceleration is 0, should there have, well, yeah, it's actually want to skip here. Right. We go back to yesterday a little bit. Where is a 0 acceleration? Here it is. Guys, here's a 0 acceleration. Guys, if there's 0 acceleration, isn't your velocity constant? Right? And yeah, this car is driving forward, but it's driving forward at a constant rate. So x versus t is not a parabola, it's just a straight line now. Okay. Right. But yeah, constant acceleration looks more like this. Okay. And then I think I was on this one, and then the bell was ringing yesterday, if I remember right. So what if you don't drop the ball? What if you throw the ball? Okay. And remember, these are all linear motion. So the ball's only ever going vertical. I could throw the ball upward, I could throw the ball downward. Okay. Now, for these particular graphs, I have certain either assumptions or definitions. It looks like I'm defining the top of the cliff as 0.0. That's why it starts at 0, 0 for either of these. So the top is 0.0. That's not always going to be the case. AP could totally say the top of the cliff is like elevation 30 meters. And then this might shift all the way up here. Okay. Also, guys, according to these graphs, which direction do they define as the positive direction? Up or down?
Down.
Down. Down is positive. You see how gravity is always pulling in the positive direction? Okay. Be ready to handle the opposite of that too. For example, guys, what if AP tells you you're at the top of a cliff that's 30 meters up? So you start up here. I'm going to call down negative and up positive, right? And you throw the ball straight up. Would that be basically this graph just flipped upside down? And look, you see what shape I'm tracing out right here? It's still a parabola. It's just like kind of upside down what's already on there. Right? Be ready to handle something like that. Right? This is kind of a basic strip down. Okay. Are you guys good with these graphs? Okay. Right. And then Oh, here, let me point out those two. Because if you throw the ball up, doesn't the ball go up, whoa, reach the maximum height, and then whoa, fall back down? Okay. And because at that maximum height, what's the instantaneous velocity equal to? Zero. Is that true here? So at the point of maximum displacement, which is right here, is that corresponding to bing, zero velocity right at that moment? Hey, look at that. See how these graphs kind of lined up? Yeah, yeah. Okay. If I take this one, now it's big. Oh yeah. So because velocity versus time graphs, very rich, information-rich graphs. You're gonna have to draw some of these graphs today for a car versus a truck. So get a good look here. So you guys know any coordinate tells you how fast at any particular time. That's the coordinates. Okay. Guys, what is the slope of this represent? Acceleration. Acceleration is a rate change of velocity. Speeding up. Okay. And because what does the accumulated area under a v versus t curve tell you? Displacement. How far? Like meters per second times seconds gives you meters, doesn't it? Okay. Well, that's v naught t plus half a t squared. Hey, that's that kinematic equation. I don't know that. Okay. Now here's one I had in my plans that we're not going to have time to get to today. Okay. But in principle, do you think if you team up with a teammate and then you drop your ruler and your teammate catches it fast as they can, and you catch it like, well, I guess I should have zero down here, right? Have 0 centimeters at the bottom. Catch it fast as it can. Boom. Suppose I catch it at the 16 centimeter mark. Does that correspond to some exact amount of time this roller's been accelerating down in the gravity field? Okay. Could you start with this and in principle solve for this t? Okay. I'm going to see if you guys can do that eventually. Not today because we're going to run out of time. But yeah, I wonder if I hand you a blank piece of paper, if you could sort of come up with a table that looks similar to this and eventually calculate your reaction time. Okay. So look at that. Okay. Car breaks to a stop. No, if I had more time, I would definitely want to do this. I'm going to cover up these graphs and have you guys go. Actually, let's sort of do this. Okay. Guys, if the car's breaking to a stop, does it have initial velocity? Yeah. Yes. What is its final velocity equal to? Zero. What basic shape do you think the v versus t graph looks like? This one right in the middle. What basic shape? Yeah, straight line. There you go. Straight line. All the way down to 0. Is that true? Okay. Now, how about acceleration versus time? What is that going to look like? Yes. Yeah, flat line constant. Flat line constant. And if the car's moving forward, if I see it driving forward, would it have a positive or a negative acceleration?
Negative.
Negative. Right? Oh, okay. What's the slope right here? Positive or negative? Negative. This guy walking downhill. That's negative. He's going downhill. That's negative slope, right? Right. Now hold on to that idea because the next poster I'm going to link that idea to something. Now the tricky one, x versus t. Is this going to be basically some version of a parabola? Do you guys think? Version of a parabola. Okay. Here's what I'll do. I know that I have the answer already embedded in the v versus t graph. I'm going to break this up into like a three. Suppose it takes 3 seconds. Can you guys imagine that? Tick, 3 seconds. Okay. The first second, you guys, that big old trapezoid right there? Isn't that the car moved a long distance? Okay. But during the middle second, during the next second, is that trapezoid not as big? Not as big? So is the car still moving forward? Yeah, just not as much. And during the last second, where it comes to a dead stop, right? Now look at the itty bitty triangle right there. Is the car still moving forward? Yes, a tiny bit. Now, if you take what I just told you and graph that position versus time, what does that look like? It's a parabola. You see, the car moved a long way in the first second. Then the next second, it's still moving forward. Right? And then the last second, still moving forward again, just a tiny bit. Is that right? And overall, that makes a what shape again? Parabola. You guys, which point? Down here at the origin or up here where the car is at a dead stop? Which point is the vertex on this parabola? Here, show of hands. How many of you think it's down here at the origin? No, nobody says that. You think it's up here where the car stops? Yeah, that's the vertex right there. This is an upside down parabola, isn't it? Vertex up here. You guess that? Yeah. Okay, I got one more poster for you guys. One more poster. Right. So this last one goes to equation, because you guys know displacement, velocity, acceleration. These are vectors. If these are vectors, that means positive, negative tells you something about the direction it's moving. They have directions associated. Is that right? Okay. So what if you have positive or negative velocity? What if you have positive or negative acceleration? Like all mixed together one giant equation. What if I have some crazy equation listed out and some of these are positive and some of these are negative, and you're like, which was moving? What's going on? Okay. Here's all the answers are right here on this table. So Yeah.
Are we going to have access to the equations during the AP test?
Okay, guys, during the AP exam, AP will give you this page right here. This page right here. So you have all these equations. Now, right now in the class, we are these top three. These top three are the three kinematic equations. Now, remember, AP writes them a little bit different. Okay. So there was a day, a few days ago, I pointed out the differences between how AP writes them and how I write them. There's like 10 different ways to write these formulas. Okay. Yeah, we're just using these three for this part of the class. Okay. Yeah, so you have access to this. You have to know how to apply these. I would recommend memorizing those three kinematic equations, but you'll have it later, right? Right. So velocity, the sign on the velocity tells you which direction you're actually moving, again, relative to something, right? Which we're about to cover relative velocity. Right? It tells you which direction you're moving. So think of plus being like forwards and minus being backwards, basically, right? Or I guess if you drop a ball off a cliff, if down is positive, maybe this is down, this is up, could be. If you define it that way. Okay? Acceleration tells you, well, something about how velocity is changing. So let's combine these signs. Because if you have positive velocity and also positive acceleration, I'm going to cover up this description right here. I wrote some description in words. Right? Suppose you're in a car. That means you're driving which way and you're doing what? Yep, driving forward. That's the positive velocity bit. And you're also, what, speeding up or slowing down? Speeding up. Aha. Okay. You guys know these two graphs right here look just like dropping a ball off a cliff, right? Same concept, right? Just moving forward, right? How about this? What if you have positive velocity but negative acceleration? Which way are you moving? Forwards or backwards? Yeah, forwards. Okay, because positive velocity. You're moving forward, but you're doing what? Break into a stop. Yeah.
We have that paper on.
Okay. This is this might not have made the. Let me see. I gave you guys something else a while back. I don't know if this one made it or not. No, it looks like it did not. Right, but I did upload a PDF. So if you go back to the very first week of Google Classroom, there's a PDF. They're all in the book. They're all in a giant book. And this would definitely be one of the pages. Okay. Right. How about is that okay? Break into a stop. Actually, guys, this bottom left quadrant isn't that exactly what this is right here? These three graphs look like these three graphs. It's the same thing. Right? How about here? Let's do this bottom right quadrant. What if you have negative velocity? First of all, which way are you moving? Yeah, backwards. So you're in reverse. Your car's in reverse, and you also have negative acceleration. Okay, so you're in reverse. Doing what? Who says you're speeding up? Yeah, because the signs match. Yeah, so you'd be moving backward more and more and more and more. You're tending the way you're already moving. Okay, here, guys. Here's the rule. Whenever the signs are the same, like plus plus, or in this case minus minus, those are speeding up conditions. Okay, so plus plus or minus minus would be speeding up, right? But if the signs are mismatched, like positive velocity, negative acceleration, you guys know how that would be slowing down. Okay, right, so that leads us to this last one. Is what if you have negative velocity but positive acceleration? That means you're moving which way, doing what? Backwards, slowing to a stop. There you go. Backwards, slowing down. Okay. Right, so again, if you see some equation listed out, you're like, what's this car doing? Okay. Yeah, think back to this table with everything wrong. Right, so you guys good with all those posters? Good. All right, so let's talk about. I have to talk about relative velocity because again, there was one or two questions that pops up. I mean, all stuff's good to know anyway. You guys are about to get a car and truck FRQ, so I'm going to do a similar type example. All right, let's say I have we're up in a helicopter, looking straight down. I see a couple of vehicles. Let's call this the black vehicle. And let's call this one the pink vehicle. So black car and pink car. Okay, see a black car and a pink car. Right. Let's say the pink car. So this is I-95. We're looking down from a helicopter. Right, I-95. This pink car. Is it okay if I use American units right now? Say this guy's going 60 miles per hour. 60 miles per hour. And this black car is in the passing lane. So let's say this black car is going 70 miles per hour. Okay. Now, because those speeds, that could be if you're inside the pink car, can you feel exactly how fast you're going?
No.
No. If you're inside the black car, can you feel how fast you're going?
No.
No. If these are constant velocities, yeah, you don't know what the velocity is. Okay? These velocities are relative to something. I'll tell you what those velocities are. they're relative to this tree right over here. That's not moving at all. This guy's not going anywhere. So if there's like a monkey sitting in the tree with a radar gun, it's like points to the radar gun. That's what the radar gun readings are reading relative to this tree, right? Right. But what about relative to the cars? So what I want to do with you guys is what's the velocity of the pink car relative to the black car? And then what's the velocity of the black car relative to the pink car? Okay, so those are common ways to write that. Okay. So what's the pink car doing relative to the black car? Okay. Now, if you're inside the black car, and maybe you don't even see the tree, all you see is yourself, and you see this pink car over here. What does it look like the pink car is doing relative to you? Yeah, isn't it? Yeah, yeah. We'd be going backwards, wouldn't it? We'd be going backwards, right? Because it's even more obvious if you're out in deep space. Because what if these are two spacecraft out in deep space? Right? Wouldn't you just be floating around? Like you may even think you're at rest. You're not even moving. It looks like this pink car is moving to the left at 10 miles an hour, doesn't it? Okay. So here's the rule. So what's the pink doing relative to black? You always take the other guy's velocity, in this case 60 miles per hour, okay, and you subtract your own miles per hour. Okay. And that gives you negative 10 miles per hour. Okay. So I would say, what's the pink car doing relative to the black car? If you're sitting inside the black car, you perceive the pink car is moving backwards at 10 miles per hour. Okay. Okay. You perceive yourself as at rest. Okay. And then the opposite would be true. The black car relative to the pink car. So if you're sitting inside the pink car now, here I'll draw a little cars here. So this is if you're inside the black car. Okay, now I'm switching over to if you're sitting inside the pink car. Okay, so what's the black car doing relative to the pink? So you take the other guy's velocity, which is the 70 miles per hour. You subtract your own velocity, which is 60 miles per hour. Okay, and it looks like plus 10 miles per hour. Okay, okay. So the pink car might think that he's at rest. In fact, if he's in deep space, he may as well be at rest. It looks like the black car is overtaking him by 10 miles per hour. Okay. All right, so you guys have that? Okay. You could also take this principle to 2 and 3 dimensions, but I think one dimension, you guys get the idea, and you can answer anything on the question. Okay. You guys got that, dude? All right, so let's move on to FRQ.